All right, welcome back, everybody. So this time, let's solve a definite integral using trig sub. So let's say we've got the integral from 0 to radical 3 over 2 of t squared over the quantity 1 minus t squared to the 3 halves dt. So the first thing we need to do is figure out which substitution is appropriate. So let's take a look quickly at our forms, the substitutions, and the corresponding identities. So we've got a form that has constant stuff minus variable stuff. And there's a sneaky radical in there, right? So if this is to the 3 halves power, that's like taking the square root cubed. So that really is a square root, isn't it? Okay, so this form seems to match this the best. Constant stuff minus function stuff. So we're going to make a sign substitution. Again, the reason why we do that is once we plug that in for u, do a little bit of algebra, we get a Pythagorean identity that reduces the radical. And this restriction is because of the cosine. All right, let's go for it. So the form that this is based on is u is equal to a sine of theta. And we said playing the part of u looks like t. So u squared is t squared. So u is equal to t. So that's going to be t equals 1 sine of theta. That means that dt is equal to cosine of theta d theta. And we're going to need new bounds, right? We're switching variables. We're going from the land of t's to the land of thetas. So we want corresponding bounds, and we need to be careful. Okay, so let's talk about our lower bound. So remember how to get that. We take our substitution statement, and we just remember that these are t values. So t goes in for t, and we get a corresponding theta. Okay, so t goes in for t, and so theta must be 0. And then for our upper, so t goes in for t, and we get a corresponding theta. Now for this one, we can use our 30, 60, 90 right triangle, or our pi over 3, pi over 6, pi over 2 right triangle. This right triangle comes from taking half of an equilateral. So say I take an equilateral triangle where all sides are 2, and then I drop an altitude or a height that's going to bisect the angle and the base. So instead of the base being length 2, that's 1. This is still 2. And Pythagorean theorem would give me 3. Again, half of an equilateral where all sides are 2. 2, 2, and 2. So when I take half, that's 1. That's still 2. Pythagorean theorem says radical 3. Okay, excellent. So for which of these angles, when I take the sine, do I get radical 3 over 2? Well, clearly this one. Sine of pi over 3 is equal to opposite over hypotenuse. So that's radical 3 over 2. So that means that theta is pi over 3. Okay, so let's go for it. So we're going from 0 to pi over 3. Okay, we need t squared. Well, t squared would be sine squared of theta. Down here, I've got 1 minus sine squared of theta to the 3 halves power. And then dt, we said dt was equal to cosine of theta d theta. So that's dt. Okay, so our next move is to use a Pythagorean identity here. And if I do that, that's going to give me cosine squared, right? 1 minus sine squared of theta is cosine squared of theta to the 3 halves. Now, if it helps, you can put that 2 over 1. You'll see that the 2's will cancel. And that's really cosine cubed. So that's going to give me sine squared of theta over, when I reduce, cosine squared, right? Because one copy of cosine, I've got 3 here, one copy will cancel, leave me with a cosine squared of theta, d theta, but that's exactly tangent squared. This looks familiar. And we're going to use a Pythagorean identity to change that into secant squared of theta minus 1. Okay, so we've got secant squared of theta minus 1 d theta. Okay, so what do we have here? So we know the antiderivative of secant squared is tangent. So that's tangent of theta. Antiderivative of 1 is theta. And no plus c because this is a definite integral. So we evaluate from 0 to pi over 3. Notice that when I change my bounds, so back here we changed our bounds. Notice that I don't go back to t's because all that information is encoded in the bounds. So by solving this, I really am solving the original integral. If you follow the chain of equalities, they're all equal to each other. So that's very, very nice. Okay, so let's follow out the fundamental theorem of calculus. So here we've got the tangent of pi over 3 minus pi over 3 minus the tangent of 0 minus 0. That's not bad because we know that tangent of 0 is 0, so that term will vanish. And for tangent of pi over 3, we can go back to our old trusty friend here, which is just right here, but why not? Such a good... I don't want theta there, do I? No, I don't want theta at all. I want my old friend back. Okay, how about pi over 3? There you are. There's pi over 6. And so that's 1, 2, radical 3. Hey, it's right there. All right, so tangent of pi over 3. So that is opposite over adjacent. So opposite over adjacent. So that's going to be the square root of 3. And that's minus pi over 3.